All right, so starting into 11.1. So today we're going to talk about vectors in the plane. Tomorrow we will finally free ourselves from 2 dimensions and go into space. And as we get to do 3D drawings, and those are always very fun. So vectors, today we're just going to introduce vectors. I know you've seen vectors before. We're going to kind of develop vectors quite a bit. Vectors are really the language of we use the language of vectors to do calculus in 3 dimensions. So we're going to, second semester, we're going to use vectors a lot. So we need to, hopefully we can get very familiar with them. And like I said, I hope everybody learns to love vectors as much as I do. And what we're going to do as we start into this is really we're taking calculus and geometry and kind of putting them together. And it's a really end up with some really cool stuff. All right, so some vocabulary, some basic ideas. Quantities that only need to be represented by a magnitude are scalars. So most of what we've worked with so far have been scalars. And a vector is a quantity that has a magnitude and a direction. So the way we represent vectors, we think of vectors as a directed line segment. So here's our vector. And we will take this idea of a directed line segment and we'll do a whole lot with it. We call the point here where our vector starts, point A, is our initial point. Just so when you see all this stuff, you know what we're talking about. And out here, point B is the terminal point. And we say that any directed line segment with the same direction and magnitude is equivalent. So it doesn't matter where they're located, as long as they have the same direction and magnitude, we say they're equivalent. When you see them in print in your book, vectors are usually bold, lowercase letters. And in handwriting, we usually use a lowercase letter with an arrow. So, and I have to be very careful, so I write my V's. Use V's a lot for vectors, and I put a little tail on my V so you can tell it apart from a U. So these would be vectors V, W, U. So those would be vectors with the little arrows. And in print, you'll see bold lowercase letters normally. They don't use the arrows, they use the bold lowercase. If we put our initial point at the origin, we say our vector is in standard position. So and then our terminal point If our initial point is at the origin and our terminal point is at some point v1, v2, then we write our vector, or we can write it as v, our vector v, equals, and we use these angled brackets, v1, v2. And we'll use a couple different notations for vectors, and I'll use them interchangeably. One you'll see more in science, and the other you'll see more in mathematics. But I want you to see both and be comfortable with both. And Mr. Lowe always double checks and says, do you teach this form of vectors? Do you write it in this form, so that we're kind of doing something similar. We call v1 and v2 the components of the vector. And we call this the component form of vector v. And then we write the zero vector is 0, 0. And one thing, it's not going to play a big role here, but it is important to make the distinction that the zero vector does not equal the zero scalar. They're different things. So sometimes it's important to notate or to realize that you're talking about a zero vector, not a zero scalar. Zero scalar would be a zero magnitude. A zero vector has no magnitude and no direction. All right, so questions on our terminology. Shouldn't be anything really new here. So some operations. Today we're talking mostly about operations, some basic operations with vectors. And we'll start with some basic operations and build some more complicated operations and get some really interesting, really powerful results. So if I have a couple of vectors, u is my components u1, u2, and v is v1, v2, and c is a scalar. To add vectors, so our vector sum, u plus v, we just add our components. And a scalar multiple, so c times v, we just multiply each component of v by the scalar. The negative v is -1. We're thinking of that as a scalar multiple of -1, and we just switch the signs on our components. And the difference, all these are pretty common sense. U minus v u1 minus v1, we subtract the components, u2 minus v2. So these are our basic operations: addition, subtraction, multiplication by scalar. We'll talk about multiplying vectors by vectors a little later, as we have to do something special. And there are a couple of different ways that we end up multiplying vectors, and we use them for different purposes. So geometrically, with vectors, we add them head to tail. So here's kind of algebraic representation. So geometrically, if we draw a picture, and this, my coordinate system is just arbitrary here, and I'll do my vectors in red. So if this is U and this is V, in blue here we would have U plus V. So to add them geometrically, we place the vectors head to tail. And then from the tail of the initial one to the head of the last one is going to be our sum. And then the difference geometrically, we would just add the opposite of one of the vectors. So if I draw a picture of that, let's see, I'm going to go this way. Let me undo that last one. I want to go this way. There we go. So if I say this now, this one is U, and this one is minus V. This quantity would be U minus V. So I just turn V around. So geometrically, to subtract them, we turn the one around and then put them head to tail. So we can define some operations, some properties of operations, very similar to operations with scalars. We have the commutative property. We can add them in different orders. We have the associative property. We can add them. We can group them how we want. Scalars distribute. So I'm not going to write out all of those properties, but vectors have very similar properties to scalars when it comes to these. When it comes to their properties, for rules for how we combine them. I just want to make sure that we understand, just so that when you hear it, the additive identity. So vectors have an additive identity. The additive identity is the zero vector, just like the additive identity for numbers is the number 0. So what the additive identity means is that U plus the 0 vector just gives us U. And an additive inverse is negative U. What that means is U plus negative U equals a 0 vector. So we call that the additive inverse. And then 0 times any vector gives us the 0 vector. So again, multiplying this by a scalar, we don't get a zero scalar, we get a zero vector. So the additive identity is the vector that you add to another vector and you get the original vector back. The additive inverse is the vector you add to, and when you add them together, you get the zero vector. For the other properties, we can group them. We can change the order of addition or subtraction. We can distribute a scalar. Those kinds of properties hold for vectors as well. So, questions so far? All right, the length of a vector. So we write the length of a vector. We use 2 bars, like so. And sometimes when I learned it, we just wrote. It's the same thing as writing 1 bar, so absolute value. In the book, you'll see it's more common now to have the double bar. I always learned it this way. I will try to do the double bar because that's what you'll see in your book. But if you see this is the same thing. This means the same thing. And our length is just the square root of our components squared. So this is just a Pythagorean theorem. And we call this length, you'll hear it called the norm of V. And the norm is kind of a more generalized idea of length. So we call this the norm. And if our length is 1, we say that V is a unit vector. So any vector with a length 1 we call a unit vector. And if we have our vector rather than in standard position, so if our initial point isn't at the origin, if we go through 2 points, so if it's between the points P1, P2, and Q1, Q2, let me rewrite that. Then the length of V is the square root, just the distance formula or Pythagorean theorem again, Q1 minus P1 squared plus Q2 minus P2 squared. So again, just the Pythagorean theorem or the distance formula. And if we have the length of CV, scalar times a vector, is just the absolute value of C times the length of V. Often what we were going to be interested in with particular vectors is finding a unit vector that is in the direction of some particular vector. So we want, if our vector doesn't have a magnitude, doesn't have a length of 1, we want to find a vector with length 1 in that same direction, because we're just interested in the direction, not the length of the vector. So to find a unit vector in the direction of v, is we just take our vector and divide it by its magnitude. So we just take the magnitude out, basically. And the other way you'll see this written is 1 over the length of v times v. And we call this process normalizing v. So the process of finding a unit vector in the direction of v is called normalizing v. So often you'll be asked to normalize this vector and then do something else with it. So let's look at a quick example of normalizing a vector. So we have v, our vector is -2, 5. And we want to normalize this. Or find a unit vector in the same direction as v. That means the same thing. So we're going to take, our process is just we're going to find this new vector v over the length of v. So what is the length of this vector? Square root of the component squared, so we get square root of 4 plus 25. We get the square root of 29. And then our unit vector, so our normalized vector v over the length of v is just 1 over the square root of 29 times -2, 5. And if I rewrite that in component form, I would say this is -2 over the square root of 29, comma 5 over the square root of 29. I'm not going to worry about rationalizing these denominators. And then if we found the length of this, if we took this squared plus this squared, our length would be 1. So this would be a unit vector in the direction of v. Or this would be v normalized. And often, it's very, very common that we will need a unit vector in the direction of some other vector because we don't want our magnitude, the magnitude of the vector getting mixed up in what we're doing. All we're interested in is that direction. All right, questions so far? Lots of little details, nothing really big, nothing really earth-shattering today. All right, so we have some standard unit vectors. We know what a unit vector is, vector with length 1. So we're going to use some standard unit vectors when we're dealing with vectors also. And our standard unit vectors are just unit vectors in the direction of our coordinate axes. And we say that I hat is the vector 1, 0. The unit vector in the direction of the x-axis. And then j hat is the vector 0, 1. So that's a unit vector in the direction of the y-axis. We can write any vector as a linear combination of our standard unit vectors. So v equals our component form, v1, v2. We can write that as a linear combination of I and j. A is just the vector v equals v1i plus v2j. So when we write our vector in this form with our standard unit vectors, we're saying we're writing it as a linear combination of our standard unit vectors. So this is the other form that we'll use for vector v. So you'll see this in science a little more, the I hat, j hat, and when we get to 3 dimensions, we'll add the k hat. You'll see this in math a little more, this one. So these two are equivalent. They're the same thing. And we said that this is the component form of v. So we say v1 is the horizontal component and v2 is the vertical component of v. All right, questions so far? All right, so now we're going to add a little bit of trigonometry into what we're talking about with vectors. So if we have our vector in standard position, so I'm going to say u in standard position, so let me draw a set of coordinate axes here, and we'll put our vector in there. Now I'll do my vector in red. So this is my vector u. And we think of its terminal point being on a circle. And we talk about this angle of rotation counterclockwise from the x-axis to our vector. We can write that u equals cosine theta sine theta. And we're saying for this particular one, the magnitude of u, if u is a unit vector. So our components are just the cosine of the angle, which gives us the x component, and the sine of the angle that gives us the y component. And if u is not a unit vector, if the magnitude of u does not equal 1, we have that u equals the magnitude of u times the cosine of our angle, the vector, the cosine theta, sine theta. And you'll also see this written as the magnitude of u cosine theta I plus the magnitude of u cosine or sine theta j. So now we can, when we start talking about angles, we can introduce what we know about trigonometry into the language of vectors. And that's going to, in a lot of situations, that's going to make our lives a lot easier. So questions here? All right, so let's look at a quick example of this idea, and then we will just have a couple more things to add for today, and then we'll be done. So let's say we have a vector magnitude 3. And makes a 30-degree angle with the x-axis. And we want to write v in terms of I and j. That's our problem. So we want to write v in terms of our standard unit vectors. So we're going to say that v is the magnitude, its magnitude times cosine theta sine theta. So all we need to do is find the sine and the cosine basically of 30 degrees. So we're going to write v equals 3 times the cosine of 30 degrees. Square root of 3 over 2. And the sine of 30 degrees? 1/2. So there's our vector. If we distribute here, we can say this is 3 square root 3 over 2 I hat plus 3/2 j hat. So pretty easy so far. Often what we will want to do, you'll be given some kind of problem, and it will ask you, one type of problem that you'll see with these basic vector operations is it'll ask you for the resultant vector, resultant force, resultant velocity, something. And all that the resultant means is that we are adding all the various vector quantities together. So we're interested in one vector that represents everything that's happening. So when you see a problem that asks you about a resultant force, resultant velocity, resultant acceleration, it just means add all the vectors together. You're just adding the vectors together. And the final result is the resultant. So again, part of what I want to do today is just get us have some vocabulary that we're all familiar with when we're working on these things. A couple of things, just a couple of details when you're dealing with resultant vectors. Often the problem, they'll give you problems that have to do with navigation. You're flying, you're sailing something, so your vectors have to do with your directions. And they'll give you the directions in bearing. So I want to make sure that everybody remembers how we measure bearing. And there's a couple of different ways that you'll see bearing notated. So in surveying and in sea navigation, your bearing is an acute angle from the north-south line. And the way you'll see this written is, for example, it will say north 30 west. And the way I read these is kind of backwards. This is 30 degrees west of north. So if we have our little compass here, this is north, east, south, west. If you forget the order. My son's elementary school friend said he remembered never eat shredded wheat. And everybody else said it should be soggy waffles. He must not have liked shredded wheat, I don't know. So 30 degrees west of north would be, a bearing 30 degrees west of north would be this bearing here. So that would be at 30 degrees west of north. So if I had something that said south 59 degrees east, this is 59 degrees east of south. So here would be our north-south line, and 59 degrees east of south would be down here somewhere. So that's what, so in surveying and in sea navigation, you'll see bearing written this way. In air navigation, they measure bearing a little different way. Air navigation is always measured counterclockwise from due north. So in air navigation, they'll say you're heading at a bearing of 132 degrees. So that would mean from due north, you're heading at off in this direction. So for air navigation, you're always measuring counterclockwise from due north. And north is 0. So some of the problems will give you angles in bearing. I just want to make sure you understand what they're talking about. So I just want to do one other quick example of taking a vector and breaking it down into its magnitude and direction. So that's another thing that we're going to want to do with vectors, is break our vectors down into their magnitude and direction. So let's say we have a vector. (3i minus 4j). We want the problem asks us to find the magnitude and direction. Direction is asking us an angle. It's asking us for an angle. So it's saying what is your angle from some particular fixed line. So our magnitude, let's find our magnitude. The magnitude of v is just going to be the square root of 9 plus 16 equals 5. So if I write, and then so this would be our magnitude. Magnitude would be 5. How would we find the direction? How would we find the angle of this a direction angle for this vector? Any ideas? Tangent. Right? So if I drew a quick sketch of this, here's my vector, and we're going 3i minus 4j, so something like this. So we're going 3 units in the x direction and negative 4 units in the y direction. So we could talk about this angle, theta, and we know that tangent theta is negative 4/3. We know we need a fourth quadrant angle. So we want to make sure that the sign, everything, that we get our sign correct. We could use inverse sine, or inverse cosine, but we'd have to make sure we get our quadrant correct. So we say that theta, like Ryan suggested, is the inverse tangent of -4/3, and this is about negative 53.13 degrees. So we'd say this vector has a magnitude of 5, and its direction is 53.13 degrees below the x-axis. So a big portion of what we're going to be doing with vectors, when we start using them as a tool, we want to normalize them. We want to find a unit vector. We want to represent them as a linear combination of our standard unit vectors to make them easier to operate with. And we will also want to find their magnitude and their direction. All right, questions on our basic vector vocabulary. Okay, tomorrow we will go into space, into 3 dimensions. And that's when things start getting really interesting. So, Carly, we have the air navigation, that angle we just found, is that what you're asking? It would be 90, so it would be 143.13 degrees. That would be our bearing. And then in sea navigation, we would say, what would this be? We'd have to find this angle. Right, so the complement, so it would be south 36, whatever, east, yeah. And for most of what we do, this is the bearing is more just so you recognize it when you see it in a problem. I would be fine with, we're going to be using more, we're just more interested in, as long as we have some kind of angle from some place that we're familiar with, we're okay. All right, yes. Can you borrow? Yes. Yeah, there's more. Yeah. These are really easy. Oh, great. There we go.